Hi, my name is Zane. I'm a PhD student from MIT. I'm excited to introduce our work, AIFM, a new system that supports file memory. This is a joint work with Malte from Ruan, Marcus from VMware, and Adam from MIT. Memory-intensive applications are widely used in our daily life. By putting the entire application working set into the main memory, they offer significant performance benefits compared with the traditional disk-based applications. However, meanwhile, memory is also a highly inelastic resource limited by the server physical boundary. Your application can never overcommit memory, otherwise they will be killed by the OS. Out of memory is very common in the real life. For example, many people have encountered this problem when using Python pandas to process large-scale data. One obvious approach is to simply over-provision your memory. For example, you can find a super large 2 terabytes memory instance in AWS. However, that's super expensive and people cannot afford it. A trending alternative is to leverage the idle memory of remote servers, and that leads to recent file memory systems. As we see in this diagram, the local server can access the file memory using the network. Thanks to the narrow performance gap between network and DRAM, file memory may offer performance comparable to the local memory. In file memory systems, when running out of your local memory, instead of killing the task, OS swapped out some data to the file memory to make room. The idea of file memory looks promising, but how does it perform on real applications? Here, we use a real-world data analytics workload from Kaggle, which is an online data science community. If we run this workload completely using local memory, we will get 100% of performance, and that corresponds to this black line. However, if we provision the file memory system with 25% of local memory, or in other words, 75% of file memory, then it wastes 70% of performance. This leads to our design goal. How can we reclaim the lost performance through a better system design? In this work, we designed a new system, AIFM, that achieves this goal. But before introducing AIFM, let's first dive into the existing file memory systems to see why they waste performance. Existing file memory systems are built based on OS paging, in which OS swaps pages between local and file memory. However, this design faces two challenges, which leads to low performance. The first one is the semantic gap, and the second one is high kernel overheads. Next, I will explain these challenges in detail. Applications read-write memory in the object granularity, while in paging systems, OS swaps memory in the page granularity. As you can see in this diagram, one memory page can contain lots of objects, which are represented using these small circles. Even if the application only accesses a single remote object, the OS has to swap in the entire page, which leads to a large amplification. OS also has no application knowledge, which makes it very difficult to make good decisions. For example, if an application is traversing a linked list, what OS is just a sequence of random memory accesses. Therefore, it's impossible for OS to do perfection. The second challenge in paging systems is its high kernel overheads. For example, when an application accesses a remote object, it has to use expensive page faults to invoke the OS handler for appropriate processing. This leads to expensive kernel crossings and convoluted kernel code paths. If the requested page is not prefetched yet, OS has to swap in the page using netbook. To avoid expensive kernel crossings, it has to busy power the netbook response, which wastes a lot of CPU cycles. An interesting thing to note here is the raw network latency is only 6 microseconds. But you actually have to spend 15 microseconds in kernel to access the file memory. As a result, existing OS paging systems achieve low performance, but high transparency, since no application code change is required. Another way to use file memory is using RDMA to manually manage objects. It is able to achieve high performance, but requires significant programming efforts. In this work, we built AIFM, which sacrifices some transparency, but achieves significant performance improvements. Let's take a look at how AIFM achieved this. The key idea of AIFM is to swap memory using a Userspace Runtime instead of OS paging. Therefore, it's possible to achieve significant performance improvements. In realizing this idea, we address the two challenges I described already. AIFM solves the semantic gap using a remoteable data structure library and avoids kernel overheads with a Userspace runtime. The two additional challenges in the bottom are also critical for achieving high performance. For the third challenge, on the local memory pressure, reclamation happens which pauses application threads and impact performance. AIFM provides a pauseless evacuator to avoid such pausing. Finally, there is still a performance gap between network and DRAM. AIFM alleviates this problem with a remote agent. Next, I'm going to introduce all these key elements concretely. First, in AIFM, the application code is running in a user-level thread. It uses our library APIs to access our remoteable data structures. In the library call, we understand what's application doing with the data structure, and therefore we can record application semantics. The semantics can be leveraged by the data structure prefetcher to swap in future data. So the application thread may never get stalled on making the data structure access. AIFM offers programming primitives for developers to build their own remoteable data structure. One important primitive here is called remoteable pointer, in which the pointer object could be either local or remote, as shown in this figure. This enables object-level swapping as opposed to the page-level swapping in paging systems. When accessing a remote object, the pointer APIs cause a runtime to swap in the object using a simple function call, as opposed to the expensive page faults in paging systems. Since network has a much higher latency than DRAM, swap-in can incur long wait time. Instead of busy polling and burn CPU cycles, AIFM runtime performs a very efficient user-level context switching to regrant CPU cycles to another application thread. Later on, when we context switch back, the AIFM runtime has already swapped in the object, so we don't waste CPU cycles here. As time goes, we use more and more local memory, and it is close to full now. Our runtime evacuator detects the memory pressure and starts proactively to avoid stalls. It easily identifies code objects using the semantic information maintained by our pointer API. In this case, the evacuator will evacuate those blue code objects to file memory. A runtime evacuator has a nice pauseless property, which means we don't have pause application thread during this process. Therefore, evacuation and application processing happen simultaneously. Now, the evacuation is finished, and we get enough free local memory space. Finally, to alleviate performance impact brought by the network bandwidth gap, we have a remote agent in the file memory side, which is able to execute light operations offloaded by the data structure library. For example, the data structure can offload the object copy command. In this case, the remote agent performs copy directly at the file memory side. Compared with a naive approach of first swapping object to the local memory and then copy locally, our offloading approach greatly reduces expensive network traffic and improves the performance. This concludes the main design elements in a file memory system, AIFM. Let's use a simple example to see how we use AIFM. Here is the original C++ code snippet. It uses 3 data structures: an order map, array, and list. The first thing we need to do is change these data structures into our AIFM counterparts. Second, in AIFM, you have to access the remoteable data structures within a dereference scope. The scope is used to ensure that accessed objects will not be moved by the evacuator. Finally, our library supports semantic hints. In this case, the array data is large and can pollute our precious memory easily. Therefore, we make a hint to disable caching on the array access. That's all for the code changes. Let's see what happens under the hood. By using the iterator interface to access the list, AIFM captures the access pattern and can accurately prefetch the list data. When accessing the hash table, our runtime will automatically cache the hard objects. Finally, with the hint, the runtime does not cache the large array data locally. Therefore, it avoids polluting the local memory. That's just a simple example, and in our implementation, we have implemented 6 different data structures. The AIFM runtime is built on top of Zhenyuan, an OSDI 19 work to leverage its user-level threading runtime and I/O stack. Based on that, we implemented a TCP-based file memory backend. In our implementation, the runtime has 6.5K lines of code, and the data structure library has 5.5K lines of code. In addition, we made around 800 lines of code changes to Zhenyuan. In our evaluation, we use a compute server and a file memory server. Both of them equip a 25 gigabits Ethernet NIC. Our evaluation focuses on answering 3 questions. First, how does AIFM perform on applications with different compute intensities? Second, how does AIFM compare to the ideal case that only uses local memory? And finally, how does AIFM compare to the state-of-the-art paging system, FastSwap? To answer these questions, we first use a micro benchmark to evaluate all systems under different compute intensities. The x-axis is the microseconds of compute per file access. Therefore, compute intensity is increasing from left to right. The y-axis shows the performance normalized to the ideal local-only version. The performance of FastSwap increases when the compute intensity increases. That's because the memory access time becomes less significant when the computation is more intensive. It requires about 50 microseconds of compute per file access in order to achieve ideal performance. 50 microseconds is too large to be shown in this figure. However, for AIFM, its performance increases much faster and achieves near ideal performance with only around 1.7 microseconds of compute per file access. That's because AIFM has a better latency hiding technique and no kernel overhead. The figure can be divided into two regions according to the application computing intensity. For the blue region, our paper offers a synthetic web front-end in which AIFM achieved a 13x speedup over FastSwap. In this talk, we instead focus on the application in the gray region. It's a more challenging case since it has a low computing intensity. In this case, we use an NYC taxi analysis workload. Here, DataFrame is a C++ open source data analytic framework, which is similar to Python pandas. It's a real workload from Kaggle, which explores different trip dimensions. The dataset is huge, which leads to a 31 gigabytes full working set size. To port the application, we modify about 1.4K lines of code, which takes 5 person days to complete. An important aspect about this application is that it has a relatively low computing intensity. Therefore, our system is unable to hide the file memory latency completely. To address this issue, we keep complex operations local and offload the very light operations, for example, copy columns, to the remote agent in the file memory side. AIFM's offloading capability helps us significantly reduce the expensive data transferring over network. Let's see how does it perform. The x-axis shows the local memory ratio used for the working set, from 0 to 100. Here 0 means we only use its file memory, while 100 means we only use local memory. The y-axis shows the performance normalized to the ideal version. First, unsurprisingly, both FastSwap and AIFM achieve ideal performance when using 100% local memory. However, when we decrease the local memory ratio, AIFM's performance decreases much slower than FastSwap. Specifically, AIFM achieves 77% performance with only 3% local memory, and 95% of performance with only 23% of local memory. Our paper also includes other experiments. In a synthetic web front-end, AIFM achieves up to 13x end-to-end speedup over FastSwap. In data structure microbenchmarks, AIFM achieves up to 61x speedup over FastSwap. We encourage you to read our paper for details. The first type of related work is the OS paging systems we've discussed, like FastSwap and Leap. The second type of work is distributed shared memory. Compared with them, AIFM provides a different memory abstraction without sharing, and is built on modern data center hardware. Finally, GC is similar to AIFM's memory evacuation. The main difference is GC aims at freeing the dead objects, while we aim at moving the live but cold objects. To conclude, in this talk, we present AIFM, application integrated file memory. Its key idea is to swap memory using a Userspace Runtime. To realize this idea, AIFM have two main components. The first one is its data structure library, in which AIFM captures application semantics. And the second one is its Userspace Runtime, which efficiently manages objects and memory with low overheads. Our evaluation shows AIFM achieved 13x end-to-end speedup over OS paging systems. Our code is released at GitHub. Thank you for watching.